Hello ladies and gentlemen, my name is Dr. Simon Schmidt and I'm head of the Department of Hygrothermics at the Fraunhofer Institute for Building Physics. Most of the heat coming into our buildings is through solar radiation, which enters the building mainly through the windows. How this physically happens and what can be done to reduce that amount of energy entering is topic of this submodule. You will use the knowledge also for the upcoming submodules. But let's start with the basics in this heat and moisture transfer lecture. Let's start. As mentioned before, most of the energy is introduced into the room through the windows. So this will be the main focus here. Especially, we will look at the solar radiation and transmission into the room. To do this, we will look at different types of windows and their effects on radiation in the room. On the left-hand side, we see a wall opening through which solar radiation I coming from the sun is transmitted. This is what we call transmission. Normally, we do not just have openings in our buildings, but install windows. So if we do so, we add a barrier to the solar radiation, and at this barrier, one part of the solar radiation is blocked from entering the room by absorption, which heats up the glass. Moreover, another part of the solar radiation is reflected at the surface of the window glass. We therefore can conclude that the solar radiation I coming from the sun is reduced by the reflection and absorption. So the total radiation entering the room is reduced. We can calculate this by reducing by using the G value. If windows are installed with more than one pane, these reduction will occur on each pane, reducing the transmission energy even more. You can see the radiation part here on the right-hand side of this slide. The factor G we have introduced is used to calculate the amount of energy which is transmitted to the room into the building. In building physics, we call the G value the total energy transmittance, which includes the primary radiation through the transmission and the so-called secondary energy supply through the heated panes by absorption. The G values are characteristics for different window types, and we can calculate or measure it. Most producers will give you the G value for their products. Let's take a look at some common G values for various types of window glazing. As we have seen before, single pane glaze reduces the radiation by reflectance and absorptions, leading to a G value of 0.75 to 0.87. This value indicates that 75 to 87% of the solar radiation from the sun will enter the room. So the lower the G value, the less energy reaches the room. If we now look at different windows with different glazings, we see that the G value can be reduced from 0.87 to 0.12 if we additionally use an external solar protection. The best insulation against radiation energy is provided by glazing with external shading. To give you an impression of how much energy still reaches the room, here is the same table again, but now with the radiation energy I arriving in the room, depending on the type of glazing. Based on a solar radiation of 3,418 kilowatt-hours per square meter in the year, multiplied by the respective G value, the radiation is calculated. Also, it is visible that glazing with external shading offers the best protection against the sun. Now let's look at the impact of different glazings on the lighthouse project in RANCHI. In order to compare different window types, we look at the base case with a single pane window, a double pane window, and a double pane window with external solar shading in order to evaluate the differences. The evaluation will be done by comparison of the solar radiation entering the room through 1 square meter of the window area. In later submodules, we will see the impact of the reduction of the room temperature, but will focus in this submodule only on the irradiation. For all variants, the solar radiation is with 3,418 kWh per square meter and year, the same as in the previous example. The physics behind the single pane glazing with a G value of 0.85 we have already seen. One part of the solar radiation is reflected, one part is absorbed, and one fraction is transmitted. By using the G value of 0.85, multiplying this with the solar radiation on the outside of 3,418 kWh per square meter and year, we can calculate the solar radiation passing through the windows, which results in 2,905 kWh per square meter and year. Introducing a double pane window results in the reduction of the G value to 0.73. By also multiplying the solar radiation on the outside with the G value, the resulting radiation to the room is 2,495 kWh per square meter and year. If we add to the double pane window an external sun protection, the fraction of the reflected radiation is increased, which results into a G value of 0.12. This results in a resulting radiation of 410 kWh per square meter and year to the room. We see that the amount of radiation is reduced significantly. To have a closer look at the reduction, we will have a look at the timely distribution of the reduction on the next slide. On the left-hand side, you see the ordinate with the solar radiation in watt per square meter, and on the abscissa, the hours of each day. Each dot of the plot represents the radiation to the room per 1 hour, calculated using a simulation program with a model of the RANCHI flat. In this graph, all days of the year are plotted. With this, the upper closing curve is the maximum radiation into the room, which is presented as a solid line later on. For the single pane window, we see that the radiation is distributed over the day and that the maximum radiation occurs at noon with approximately 3,100 watt per square meter. In the same manner as before, the next variant we calculated was the double pane window, which is displayed as blue dots. The red line in the graph shows that the closing curve from the single pane window as a reference. We see that in comparison to the single pane window, the radiation entering the room is reduced over the whole day, as well as the maximum, which occurs also at noon, reduces from 3,100 watt per square meter to 2,700 watt per square meter. If we now add a solar shading to the double pane window, we again see a reduction of the solar radiation indicated, now as the green dots. For the comparison, the red and blue closing curve of the two other variants are drawn into this graph. By adding a solar shading to this window, a reduction of the maximum solar radiation into the room to approximately 3,650 watt per square meter is achieved. Moreover, we also see that the maximum is no longer a peak but a period between 8 and 4 p.m. The differences are also visible by just looking at the three closing curves, as you can see it here. So let us conclude these findings. In our simulation, the use of different glazing is noticed as follows. The graph shows that the energy that arrives into the room distributed over a whole year. while the red curve stands for a single pane glazing and still gives the highest values, is to be seen with the two pane glazing already that the energy transmission into the building decreases significantly. With the double pane and external blind, it's even better. In summary, it can be stated that the choice of glazing and window type can influence the radiation arriving into the room. Each pane of glass that is additionally placed in the windows opening reduces the radiation coming into the interior. However, by far the best protection against radiation is provided by external solar shadings. Therefore, for regions with high irradiations, such as sunshade should be planned as a standard to avoid overheating into the building. Thank you for your attention and goodbye.